but it is snowballing out of control here. All right, so anyway, I got some video. I don't know how it's all going to blend together. I'll just do it again, period 7. So anyway, how do we find the horizontal asymptote? All right, so I'm going to kind of steal my own thunder. You have your own rules here that rely on stuff that you learned in pre-calc, so memorization. So let's do it a little bit differently. So I'm gonna make a little note here. To find the horizontal asymptote, determine the limit as x approaches infinity, or negative infinity actually, it won't matter, but if you have a choice in the matter, just go with the positive one, of your end behavior model. All right, so for example, I'll steal example A here. Limit as x approaches infinity of 1 over x is going to be 1 over infinity. Now, the thing you got to be careful about with limits is you're not looking for what a limit is. You're looking for what a limit is going to, or what a limit is approaching. All right. So when we use an equal sign at all, it implies in almost every case equality. It's saying the limit is equal to this. The limit will never be equal to something. The limit is going to something. The limit is approaching something. So 1 over increasingly large denominators is going to what? What number would 1 over increasingly larger and larger denominators be approaching? 0. All right. And that's something you could verify. Start with 1 over 1. That's 1, right? 1 over 2, smaller than 1. 1 over 3, the denominators are getting bigger, but the fraction's getting smaller. 1 over 4, 1 over 5, 1 over 10, 1 over a bazillion, teensy tiny, right? It's getting closer and closer to 0. All right, so what we just learned from this is that the horizontal asymptote for that original function is y equals 0. And you would say maybe, but it is snowballing out of control. It's entirely possible. All right, so anyway, I got some
rules
video.
are so much easier.
Why would I ever do it this way? Together. I'll just do it again, period 7. And my answer to that would be, so anyway, the rules are easier if you remember the rules. How do we find, right? If you already have to come up with the end behavior model to find limits, so I'm going to kind of steal my own thunder. You have your own rules here. So that's a little bit of an extension. I stole my own thunder a little bit in pre-calc, so memorization, but so that's okay. Let's do it a little bit differently. So I'm going to make a little note here. To find the answer for the end behavior model, we got that a long time ago. The horizontal asymptote. Determine the limit. Right. But for us, it's a means to an end. As x approaches infinity. And so that's where everything else came from. Or negative infinity, actually. It won't matter, but if you have a choice in the matter, just go with the positive one. Of your end behavior model. You do, but it won't impact the extreme values of x. So it's irrelevant. All right. So for the EBM, for example, in part B, I'll steal example A here. We'd be looking at y equals limit as x approaches infinity. We're taking this guy and dividing it by this guy. 1 over x. Negative x squared is going to be 1 over infinity. Simplifies down to just y equals x. So that's your end behavior model. The thing you got to be careful about with limits is you're not looking for also find the limit is of this original function as x approaches infinity to, or what finding the any horizontal asymptotes if they exist. So like I said, when we use an equal sign at all, it implies in almost every case in a sec equality. It follows the same general theme. You could verify this against your calculator, and the limit is going to something. The limit is approaching. That being said, so this is probably as good a time as any to increasingly large denominators. The x84 graphing calculator. It's up to you if you want to get it. What number would it's one
there's
over
a free version
increasingly
and then
larger and larger
denominator
version which costs $5. The free version allows you to have you can work like one,
and that's something you could verify.
Do some minimal things, but it's
start with 1 over 1.
Right,
that's
so
1,
basically
right? 1 over 2, smaller than 1. 1 over 3.
With your
the denominators are getting bigger, but the fractions getting smaller. 1 over 4, 1 over 5, 1 over 10.
So if you're one of those folks
bazillion, teensy tiny, right?
Who generally needs to borrow one of my calculators for like tests and things like that,
right? So what we just learned from this is that the horizontal asymptote, even if you got that original function,
that's $5 compared to whatever
is y equals 0.
So
and you would say maybe
app. And
I don't know.
I said,
it's entirely possible.
So. But it's pretty cool.
The rules are so much easier. Why would I ever do it this way?
Calculators that we have. It's just
and my answer to that would be, yeah, the rules are easier if you remember the rules.
I'm just going to type in the second function and just
if you already have to come up with the end behavior model to find limits, you might as well use it for the other thing as well.
Right?
So that's a little bit of an extension. I stole my own thunder a little bit for the next
free
page,
version has some
limited
features. So it'll instead of letting you use like 10 y equals equations at the same time.
The answer for the end behavior model, we got that a long time ago.
So
it definitely restricts you, but it might be enough. Like if you're in a pinch,
you're in a library, you want to crank
for
out
us,
some
it's a
math,
means to an end.
have a calculator for something else. And so that's worst case scenario, download the free version. It's probably going to do what you need it to do.
All right, so just a thought. Anyway, so I'm going to graph the original. And I'm going to graph my behavior model.
It won't impact the extreme
color,
values
so that's nice.
So it's
there is no need for windows and zooms. B, just because when you hit graph, it's touchscreen.
We'd be looking at
y equals. There's that. We're taking this guy and dividing it by this. So if you really want to explore functions,
negative x squared,
this might be the way to go.
Over negative x.
You know, you could kind of really get a good feel for things.
Simplifies down to just y equals
by
x.
playing around with this, you can see that the blue curve, which is the original function, the rational function, is definitely approaching the red line.
We can also find the limit
and you
of this original function as x approaches
your
infinity,
x values and see
finding any horizontal asymptotes if they exist. But like I said,
it's more of a public service thing because I
for the next page, which we'll get to in a sec. But it follows the same general theme. You could verify this against your calculator and go from there.
I had a YouTube.
That being
my
said,
YouTube account. I upload.
This is probably as good a time as any to talk to you about.
Put effort into it.
The X84 graphing calculator.
Before I get to the
it's up to you
threshold
that would actually get me money. So
it's because
there's a free version and then there's a pay version which costs $5.
It didn't matter.
The free version allows you to have just like you can work like one function at a time and do some minimal.
Well, I guess the issue is if you have 700
subscribers
and nobody's watching
it, basically allows you to do some things that you would do with your graphing calculator without having to
I appreciate that.
Calculator around. Right, so if you're one of those folks who generally needs to borrow one of my calculators,
I sent a document to the print shop.
But you don't want to go out and get your own.
I don't know if you saw it, but I have the sign that says smash that. Even if you got the pay version, that's $5 compared to whatever the calculator costs.
Printing it up in color,
so it's the X84 app.
I could hang it up, and
like I said, there's a pay version of it also.
That'll help.
But it's pretty cool. It's got the same layout as the calculator.
Smash it right through the wall.
It's just touchscreen. So I'm just going to type in this second function and just show you a little bit about how it works. I get no money for this.
What's the difference between the paid and free?
It's the paid version is an unlocked version that does everything. The free version has limited features, so it'll instead of letting you use like 10 y equals equations at the same time, it'll only let you use like 1 or 2. So
it definitely restricts you, but it might be enough. Like if you're in a pinch,
you're in the library, you want to crank out some math, you don't have a calculator. At worst case scenario, download the free version. It's probably going to do what you need it to do.
All right, so just a thought. Anyway, so I'm going to graph the original, and I'm going to graph my end behavior model. It's color, so that's nice. There is no need for windows and zooms, just because when you hit graph, it's touchscreen. So there's that. So if you really want to explore functions, this might be the way to go. So you could kind of really get a good feel for things. But by playing around with this, you can see that the blue curve, which is the original function, the rational function, is definitely approaching the red line as it gets more extreme in terms of x. And you could expand your x values and see that that's definitely true. All right, so like I said, it's more of a public service thing because I get no money for anything that I do. Yeah, I had a YouTube my YouTube account. I upload and I put effort into it, and then they demonetized me right before I get to the threshold that would actually get me money. So because I wasn't getting enough views. Yeah, it didn't matter that I have like 700 subscribers. Like, I guess the issue is if you have 700 subscribers and nobody's watching it, that's probably a red flag. So,
I'll start watching it.
yeah, I appreciate that. So I sent a document to the print shop. I don't know if you saw it, but I have the sign that says "Smash that like button." I have that sign. He's printing it up in color and laminating it so that I could hang it up in the classroom, and maybe that'll help. I don't know. Just smash it right through the wall. So, but yeah, so it is a collaborative thing. Anyway, the reason I'm bringing that up is because she took a lot of time and effort to put this little section together that really walks you through how to visually determine infinite limits, and it really actually does a very great job of that. But what I found in the past is that people just like gloss over this little section and just move on and say, "Well, I'm just going to tackle some problems," and then they come back later on and say, "I don't know how to find limits when infinity is involved graphically," and then I say, "Well, it's there. It's on page whatever this is 9," and so. When you look at it, if you actually look at it, it makes perfect sense, and like all your questions are answered. So I do recommend that from time to time, take a peek at this little section because odds are your questions are going to be answered. All right, it goes through pretty much every case that you could possibly imagine. All right, so looking at number 1, where it asks you to find each of the limits, we're doing this as the limit is approaching infinity. Let me get the little highlight action going there. All right, you got to be careful. When you're dealing with limits, you could have limits as x is approaching infinity, and you could have limits as x is approaching a constant. It has happened before, more times than I care to admit, where a student sits down and takes the first unit test on limits, and then answers every single question as though it's a limit as x approaches infinity, even the ones where x is approaching like 2. So yeah, they got half the test wrong, just because they didn't open their mind to the fact that there are different circumstances that require different approaches. All right, so I'm going to show you an approach. You can't walk out of this class being like, that's a great approach. I like that. I'm going to use that all the time. My answer to that is you don't have that right. You can't say, I'm going to use this approach for every single thing, because it won't apply in every single situation, all right? So you have to be open to the other approaches because sometimes those are going to be the right way to go as opposed to this. All right, if you see an infinity, the first thing I want you to write down on paper is 3 little letters, E, B, M. All right, you're going to find the end behavior model. And you're going to pop in y equals, then you're going to take the coefficient, sorry, not even the coefficients, the terms, the leading terms, top and bottom, 5x and x. No matter where they are, maybe they're not in the front, maybe they're in the back, but you got to grab the ones with the highest powers. Simplify. So you get y equals 5, all right? What you then do is find the limit as x approaches infinity, the same infinity as is in the problem. So if it's going to negative infinity, you're going to negative infinity. If it's going to positive infinity, you're going to positive infinity. of just the EBM. This should sound familiar because, fun fact, when you're finding the limit as x approaches infinity, you're finding the horizontal asymptote. Right? So one begets the other. So it's kind of weird that you learn horizontal asymptotes first because the explanation behind why horizontal asymptotes exist is a limit-based explanation. But you needed to learn horizontal asymptotes in order to understand limits. So it's so strange, but that's the way of it. The limit of a constant is the constant. And that's because there's nowhere for me to plug in that infinity. It's a substitution-based approach. When I'm applying a limit, I plug in the limiting constant, whatever it is, in this case infinity, I plug it in for x. There's no x. Nowhere for me to plug that infinity in. So the result is just 5. So the limit as x approaches infinity of this function is 5. If you were to go back to pre-calc, strip off the limit. So you're sitting in Ms. Tong's class or Ms. Hamilton's class, if you're in GAP, and you're given f of x is equal to 5x plus 4 over x, the question might say, identify the horizontal asymptote. You would have come up with y equals 5. That was your end behavior model, all right? It also happens to be the infinite limit, all right? So it's doing double duty, which is great, because you're relying on something that you already knew to get the job done, all right? So let's take a look at number 5. We'll do numbers 5 and 6. All right, and then I'll let you loose. What is it, 10:01? 10:07, okay. Yeah, so plenty of time to get some stuff done. All right, EBM, because I see an infinity as my limiting value. All right, if I saw anything other than infinity, it's a different approach. We haven't gone over that different approach. You may have seen it last year. If you didn't, no problem. We're going to talk about it tomorrow. All right? So just understand if you see x is approaching something else, you're doing one of two things. You're either going back to what we did yesterday, creating the graph and doing it that way, or you're sitting tight and waiting for me to go over the algebraic approach. All right? So y equals, we got x squared over x, right? And that's going to give me an x. Then we're going to find the limit as x approaches negative infinity of x. All right? So, same idea as the last one. If I can plug in the negative infinity for x, I will. I can. There's an x. I can replace it with a negative infinity. So my answer here is negative infinity. All right, so that actually supports the idea that this function would not have a horizontal asymptote because as x is going out to negative infinity, y is going down forever. A horizontal asymptote means that the function is going to level off somewhere, right? If it's going down forever, how could it level off? You with me? I thought you would be. All right, and so the last one I want to go over is number 6, because I'm giving you the 3 different flavors. All right, so we have y equals, we got the 3x, we got the x to the 4th, and that simplifies down to what? 3 over x to the 3rd. So we're going to find the limit as x approaches infinity of 3 over x to the 3rd. Do some direct substitution. Spoiler, that's pretty much how we do it when x is approaching a constant, but more on that tomorrow. So 3 over infinity cubed. What's that going to be? 3 over something that's getting larger and larger and larger. And then larger even still.
Infinity.
Not infinity. It's getting smaller and smaller and smaller, right? It's going to go to 0. Yeah, fraction's getting smaller and smaller and smaller, right? So eventually it'd be like 3 over 1,000, 3 over 10,000, 3 over 100,000. Now, worst case scenario, because I do understand that there are some memorizers in here. If you're a memorizer, infinity on the bottom, limit 0. Infinity's on the bottom of the fraction, limit 0. All right, everything else, it is what it is. But infinity on the bottom, limits equal to 0. All right.